Okay, students. So my name is Palak Patel. I am working in the Mahatma Gandhi Institute of Technical Education, a research center, Navsari, in Civil Engineering Department. I am going to teach you the subject is design of reinforced concrete structures. Okay. In this lecture, we will cover Module 4, Design of Flat Slab. So shall we start? Okay, I have one announcement here. Before starting the lecture, I create one Google form which I share in the description. We are put a description. Okay, sorry. I will share a link in the description, so you can fill this Google form and ask any question. If regarding this video, if you don't understand any queries and any questions, you can put in this, and I will definitely contact you by your email within a week. Okay. So in this lecture, we will cover introduction. In the introduction, we will cover advantages and disadvantages of flat slab, types of flat slab, and design method, direct design method. And we are going to design two types of flat slab, like first is without drop and column head, and second is with drop and column head. So shall we start? First things is introduction. Introduction, we require why we require a flat slab. Imagine there is a beam. If a slab length is so high, so big, okay, length and width is so high comparatively regular slab. At that time, beam depth is increasing. Okay, beam depth is increases because the slab is too much bigger, and the slab is big means a load is higher. So by the load, we resistor load, we require maximum depth of the beam, and this maximum depth will effect on our headroom. Beam of a great depth reduce the headroom of a ceiling height, right? So at that time, if we required a maximum height of the building, we cannot achieve this. In some places like warehouses, offices, or larger area, this required larger ceiling height at that time, and column length is minimum. Distance between the two column is maximum, because we not in the warehouses we cannot provide columns at regular intervals. So distance between the column increase means slab increases, and if slab length and width increase means load increasing, and load increase means beam depth increase. So at that time, in the warehouses, in the office, we provide a flat slab for reduce a beam height, right? And we can provide against flat slab, we can provide conventional tree beam, flat slab, or grid slab, but we can provide flat slab. So we are going to learn flat slab design, right? So what is a flat slab? In a flat slab, RCC slab built monolithically with supporting columns and reinforced in a two or more directions. Monolithically means in one time. Okay, column and slab constructed at one time. Okay, and beams are not provided for the slab, means in the flat slab we don't have a beams are there, right? And slab load is carried by a slab which directly transmitted to the column, means in the flat slab we don't have a beam other, right? Now we have some advantages of flat slab. First advantages is give a less story height for the given clear height of the floor. Formwork is simple because there is no beam, you have to provide some flat plates are there. Construction of flat slab is simple and speedy. Plain ceiling area because there is no beam, so we can see a plain ceiling area, saving materials and more access to a daylight, right? Then after some disadvantages, first is larger thickness of slab, larger thickness of slab. Then after, lack of resistance of lateral loads. These are the disadvantages of flat slab, because if there is no beam, there is no beam means a thickness of slab will be increased, because load transfer mechanism is changed. Load transfer mechanism is changed. Imagine there is no beam means load will be transferred from the beam to column, no, not beam to column, slab to column, slab to column. That means required more reinforcement, because transfer of load is not a great thing. Okay, it's not easy to transfer a load from the slab to column, it's not easy, so we require more reinforcement. If reinforcement increase means thickness of slab will be increased. Okay, and this thickness of slab will be increased in the load. So these are the disadvantages. And lack of resistance of lateral loads, lack of resistance to a lateral loads such as wind load and earthquake loads, right? Now we have three types of flat slab. First is without drop and without column head. Okay. When we record this required for the lighter load, carrying lighter load. And second is with column head but without drop. So for the resist bending moment we provide a column head. The last one with a drop and with column head. When larger shear force is developed, we require a drop. You can see it's a drop here. This green line is a drop and here is a column head, right? So column head is used for the resist bending moment, while drop is used to resist shear force. Simple logic, right? So in this lecture we are going to learn without drop and without column head flat slab design, and with drop and with column head flat slab design, right? Now we have to design method. Is design method of flat slab. We have two design method. First is direct design method, we call it DDM, and second is equivalent frame method. So in this method, empirical coefficients are used to find out a design moment at various locations. This definition is not need to remember these things, but you have to understand there's two types of design method. First is direct design method and second is equivalent frame method, right? In the direct design method, empirical coefficients are used to find out a design moment. Means we use some coefficient to find out design moment at various locations. But in the equivalent frame method, structure is divided into plain continuous frame and analysis is carried out. Structure is divided into plain continuous frames. Then after we analyze it. So in this lecture we will cover direct design method. Means we are using empirical coefficient for the design. Now we have some important definition. First is column strip and the second one is middle strip. So why we require column strip and why this is middle strip? Imagine flat slab have a no beam. There is no beam in a flat slab. So how we transfer a load from the slab to column? By this column strip and by this middle strip. By this column strip, your load can be transferred from the slab to column. In the middle strip, the load can be transferred from the middle to column. Simple phenomenon. But this is column strip, there is required more reinforcement compared to middle strip. Because column strip is particularly transfer load from slab to column. At that time, column strip required more reinforcement. So in the design strip, column strip width is 0.25 L1 or 0.25 L2, whichever is smaller. So L1 is a span in a direction moment are being determined, or L2 is span traverse to L1. Simple logic, L1 means the longer span, L2 means shorter span. Simple logic are there. L1 means longer span, L2 means shorter span. Right? But column strip width is also depend on the drop. Column strip width is also depend on drop. How? When drop is present, then the width of the column strip shall be taken as width of drop. Means column strip and drop both are interconnected. Okay? Column strip and drop both are interconnected. Width of column strip is same as width of drop, and width of drop is same as width of column strip. What is middle strip? Middle strip means a part of slab bonded on each other is opposite side by a column strip. And panel is a part of slab bonded on each four side by the center line of column. Now this three definition you can see in this figure. Right? So it's column strip. Okay, here is also column strip, here is also column strip, right? And this orange line you can see, this orange is a drop, and the green is a column, right? And in between this, lecture में है लेक्चर में जो तो 22-23 में जो सामने तृप्ति में सॉरी okay, so you can see it's a middle strip. Here is a middle strip, here is a middle strip, here is a middle strip, right? And panel, how we describe a panel? Panel is simple definition, connection between column to column center line. This is called a panel, right? And this is called a second panel, right? So panel is simple definition, center line between column to column is called panel, and this is column strip. Center one is middle strip. So we in the flat slab design, we design column strip different and middle strip different, right? We design a column strip separated and middle strip separated, right? Because both the working load is different, right? Load transfer mechanism is different, so design is changed. Now property of flat slab components. Some things are fixed. From IS 456-2000, some things are fixed, like thickness of flat slab is minimum 125 mm thickness, not less than 125 mm, right? And this thickness is decided by deflection criteria. We will discuss it when we start in the example. What is deflection criteria? But this thickness of flat slab is depend on the IS 456-2000. Right? And if slab contains drops, then after the width of at least equal to 1/3 of respective span, means drop width is 1/3 of the span, right? Second, drop is reduces shear stress around the column support, reduce negative moment. Why we provide a drop? Because this reduce shear stresses and reduce negative moment. And dimension, length is 1/3 of the panel length and thickness 1/4 of the thickness of slab. Because You can see there is a drop dimension, length and thickness is depend on the slab, is depend on the panel, right? Now some condition will be fulfilled because we are using the direct design method. Some condition has to be fulfilled. So first condition is 3 continuous span of each direction. Panel shall be rectangular. Ratio of the longest span to the shortest span within the panel shall not be greater than 2. Ratio of the longest span to the shortest span within a panel shall not be greater than 2. Successive span in each direction do not differ by 1/3 of the longer span. Successive span in each direction do not differ by 1/3 of the longer span. And design live load shall not be exceed 3 times the design dead load. So these 4 conditions, you have to remember these things because these things can be asked in an exam, right? So just remember these 3 lines. Now we have some total design moments. First, if design moment is W ln by 8, W ln by 8 from the IS 456 2000 page number 55. These are the flat slab design moment. M0 is total moment, W is design load on area, ln is equal to clear span extending from face to face of column. Clear span is from face to face of column, right? Now distribution of moment. We found a moment, okay? First we found a moment M0, but we have to distribute this, right? So distribution by IS 456 page number 55, there is a negative design moment is 0.65 M0 and positive design moment 0.35 M0. Okay, now we can see here, okay, 0.65, 0.35. You can see is the internal span, slab, L1 length, column here, 0.35 M0, 0.65 M0. Okay, now imagine there is M0 means 100% moment. Okay, now here is a center, you can say 35% moment in the center and 65% moment at the end. Simply in the internal span, that is so simple. Means 100% moment is distributed by 35 and 65. 35 in the center and 65 at the end. In the internal span. Remember, it is in the internal span, right? Now there is a change in the end span. Interior negative design moment, exterior negative design moment. This is the equation. 0.75 minus 0.1 divided by 1 plus 1 divided by alpha c m0. Exterior 0.65 divided by 1 plus 1 plus alpha c m0. Now here is interior and what is exterior. What is interior and what is exterior? You can see is the external span, means at end span. Here is the interior and here is the exterior. You can see interior positive, exterior negative, right? Now positive design moment. So you can see here interior negative, exterior negative. Same thing, positive design moment. Positive design moment equation is 0.65 minus 0.28, 1 plus alpha c m0. Now we can find out fc. We need alpha c. Alpha c means a fractional stiffness of exterior column and fractional stiffness of slab at a joint, means kc and ks. By this alpha c we can find out pattern loading. Okay, we will understand things while we calculate exam. These are the moment of external span. You can see. Now we starting the example. First example is without drop and without column head. So we are going to learn an example. So first is a design an interior panel of a flat slab of panel size 4 by 6 meter to 6 meter. 4 by 6 by 6 meter. 4.5 by 6 meter. Without providing drop and column head. And size of column is 300 mm by 400 mm. Live load is 4 kg per square. Floor finish 1 kg per meter square. Height of column is 4 meter above and below slab. And use M20 grade concrete and Fe415 steel. And this type of exam is asked in May 2017 to November 2018. This type of example will ask 2 times in a row. Now here is a figure. You can see the dimension 6 meter, 4.5 meter is the dimension of one panel, and this is the center line of the column, and we are going to design this interior panel, right? And this is column size 400 by 300 mm. Okay. So first step is found the depth of slab. Depth of slab means the thickness of slab. We can find the thickness of slab by IS 456 2000 page number 37-38, right? And on this page we can find out length and depth ratio. Length and depth ratio. And this equation we have to find out from this IS 456 2000 page number 37 and 38. Let's check. How we find out the depth of the slab? We can find out depth of the slab by the control of a deflection, right? Control of a deflection. Deflection control can be calculated by a depth and span ratio. Depth and span ratio. By this two ratio we can find out a depth. Okay. So basic value of span is effective to depth ratio for a span up to 10 meter. If cantilever portion there is 7, simply supported 20, continuous 26. Okay. So we have the continuous, so 26 into modification factor. So length and depth ratio can be controlled by a deflection by 26 into modification factor. Okay. So there is the equation. So by the IS 456 2000 page number 37-38 we can find out length by depth ratio is equal to 26 into modification factor. So for the fat slab L is a longer span, but for the regular slab L is a shorter span. Now we have to find out D. Now imagine there is a length we are going to find out depth, but we require MF, modification factor. So when we find out MF from IS 456 2000 clause number 31.2 page number 53. On this page number 53 clause number 31.2 we have one chart. Okay, first remember this value. Okay, first of all remember this value, PT is 0.4%. Okay, remember this, we assume PT is 0.4%. so by this PT value we can find out MF. From where? From the page number 53. Let's check. Okay, so by this chart we can find out modification factor. First I have told you to remember one thing, there is a percentage of tension reinforcement PT. We assume is 0.4. So this line we have to follow, 0.4 graph, right? And what is Fs? Now how we calculate this I will discuss in earlier lectures. You can check this why we calculate Fs and how. So in this line we going for the Fs 240 because IS 4 because we have a Fy 415. So by this chart this graph will merge here. matches here. So right, so your value between 1.2 to 1.4, so it's the approximate value, it's the approximate value. So 1.2 to 1.4, so I assume 1.3 modification factor. Okay, I explained in the graph, you can see. So by this all the value we are going to put this in this equation. So by this solving equation we can find out depth 177.51 mm. These are the depth. Minimum depth is okay. So minimum depth is required 125 mm. We discussed in the theoretical concept. Okay. So provided overall depth is 200 mm. Okay. So small d is effective depth is 200 minus 5 by 2 minus clear cover. Assume 10 mm diameter bar. That's why depth is 175 mm. Effective depth. Effective depth in a longer direction 175 mm. Effective depth in a shorter direction 165 mm. So our dimension is fixed. Slab dimension is fixed. One panel slab dimension is fixed. Now we are going to find out step 2 load calculation. We are going for the step 2 load calculation. So first on the slab we have a self weight of slab is 0.2 into 25 into 5 km square. Second, floor finish 1, live load 4. These two are given, 1 and 4 is given. So total load is 10 kN per meter square. Total load is 10 kN per meter square. That's why factor load 1.5 into 10, so 15 kN per meter square. Here is 0.2 is the thickness and 25 with the density, so 5 kN per meter square self weight. 5 plus 1 plus 4 is 10, right? So dead load is 5 plus 1 is 6 and live load is 4. Why we describe this? Separate dead load and live load, because we require to find a pattern loading. Okay, so that's why we calculate dead load differently and live load separately, right? Now we are going for the step 3 calculation of stiffness and alpha C. Calculation of stiffness and alpha C. So calculate stiffness along longer direction. We have for the column. So KUC and KLC for EI by L. These are the equation of the stiffness for EI by L. Well, L is a 400 mm height of column. Okay. In the example, you can read it. There is a length of the column. Height of the column is fixed. Above and below both are the 4 meters. So 400 mm. So put the value in the equation 4. E will be as it is 300 direction. 400 by 300, so 300 by 400 cube, so 4000 into 12, so 1.6 into 10 raised to 6 EI, 1.6 into 10 raised to 6 EI. These are the stiffness of column. Same thing we have to do for the stiffness of slab, 4 EI by L, 4 into E into 4000. Okay, right? So 2 into 10 raised to 6 EI. 2 into 10 raised to 6 EI. So alpha C is equal to sigma Kc plus divided by sigma Ks. Sigma Kc means stiffness of column and sigma Ks is stiffness of slab. Okay, and this equation we found it from IS 456 2000 page number 56. IS 456 2000 page number 56, right? So put all the value in the equation. This multiplied by 2. Why? This equation summation of sigma Kc plus sigma Ks is multiplied by 2. Multiply by twice, because we have 2 columns in one direction. Okay, imagine here is a panel and is a longer direction, this by 2 and that by 2. Okay, that's why we multiply by twice, because we have 2 columns in same direction and 2 slabs in the same direction. So 0.8 is calculated. right? Same thing for the sorter direction. For the sorter direction, KUC, KSC, 4EI by L, 4, okay. I is BD cube by 12 here. I is equal to BD cube by 12, right? So BD cube by 12. So 0.9 into 10 raised to 6. Ks is equal to 4 EI by L, 4 into 6000 into 200 cube divided by 4500 into 12. So for the slab is 3.55 into 10 raised to 6 E. So alpha C is by this equation 0.254 calculated. So alpha C, and both for the shorter and longest direction we find out, right? Now we are going to for the check for correction due to pattern loading. Check for the correction due to pattern loading. We have to calculate this because moment will be distributed. So that's why we have the ratio L by D is 0.6.5. So this condition is given in IS 456 2000 clause number 31.4.6 page number 56. Let's check this. So by this equation you can see there is a check for the pattern loading is required because ratio is more than 5. Live load and death ratio is more than 5. So we are going to calculate loading, pattern loading. So we are going to along a longer dimension as well as shortest dimension. So longer dimension, first we have to find out how we calculate this. We can calculate it by IS 456 2000 page number 56 table number 17. Let's check what we have to require at that time. Okay, so here is a table 70 minimum percentage value of alpha C. So imposed load and dead load ratio, we need it. We need y ratio L1, L2 and L1 and value of alpha C minimum. So first we calculate alpha C value. Right now we are going to alpha C value by code. The first step we calculate alpha C value by a calculation. In this step we have to calculate alpha C value by code, which is minimum required. If this difference between calculated and minimum value required, we have to correction in between bending moment and positive bending moment. Okay. So first imposed and dead load ratio is 0.5. Okay, is fixed. Imposed and dead load ratio is 0.5. And ratio of L2 by L2 0.5 to 1. So alpha C value is 0. So let's check. We require L2 and L1. L2 and L1. Ratio of L less. So you can see there is a chart table number 17. Okay, I just separate this chart. Why? Because we have a two condition here: live load and dead load ratio, and as well L2 L1 ratio. Okay, so here we have to fulfill these two conditions to find out alpha C minimum. Okay, so live load death load ratio is 0.66. So here is 0.5 and 0.1. So alpha C minimum value in between these two values. Same thing for the L2 and L1. So 0.5 is 0.5 to 2. So L1 and L2 ratio is in between these two value, alpha C is okay. But if 0.1 is here, so 0.5, 0.8. So alpha C L1 L2 ratio is 0.75. So alpha C value in between these two, right? So now we have to find out in between this 0.5 or 0.8. We have to find out nearer 0.75, right? So let's find out. So here is okay, L1 L2 ratio is 0.5, 0.8, same alpha C minimum 0.6, 0.7. So 0.5, 0.8 is difference 0.3, 0.6, 0.7 is different 0.1. Okay, and 0.25 is the difference between 0.5 minus 0.75, right? So this alpha C minimum is 0.063. So alpha C minimum 4.75 is 0.683, right? Right. So what, which chart we find out? We have find out this, okay, 0.5 and 1 4.75 0.75, we have a value is 0, and here 0.683. Okay, so 0.5 as a value is, you can see in the chart there is a 0 to 2, right? So 0.75 is always 0, but in the 1 we have a two different value, 0.5 and 0.8. So we have to find out alpha C minimum for the 1, for the 0.75 L1 L2 ratio. So 0.683. But there is a one more condition here. A live load and death rate ratio 0.67. Is the live load and death rate ratio is 0.67. So in between this 0.67, so we have to find out this same condition here, same formula. Okay, live load death rate ratio 0.51, alpha C minimum 0, 0.63, 0.5 difference. So alpha C minimum is 0.233, and alpha C calculated is more than alpha C minimum. So no correction is required for the longer dimension. No correction is required for the longer dimension because alpha C we calculated earlier is greater than alpha C minimum, which is required. So here is safe. Now we are going for the shorter dimension. We have to check for the shorter dimension. Same formula, same table, same equation and same method. Look here. L1 L2 ratio 0.25 to alpha C minimum 0.8. But here is a L2 L1 ratio will be changed because we have to get the shorter dimension, so dimension will be changed. Okay, look at here. L2 6000 and 450. In the longer direction 450, 6000. Right? So this value will be changed L1 L2, but live load and death rate ratio are the same. So alpha C minimum 0.75 to 4 difference. So alpha C minimum for the 0.25 to 2 is 0.644 for the L1 L2 ratio. But live load death rate ratio is 0.67. Okay. So WD alpha C 0.5 1, 0.5 is 0, 1 is 0.844, difference 0.5, 0.5 minus 0.84 to 0.7, 0.22. Alpha C is 0.283, sorry 285. So alpha C is calculated 0.254, which is less than alpha C minimum. So correction for the pattern loading is required for the shorter direction. Because alpha C calculated is lesser than alpha C minimum. At that time we require pattern loading. Right? So for the pattern loading we have an equation from the IS 456 2000 page number 56. Let's check. Okay. So here is equation. BS 1 plus 2 minus WD minus WL divided by 4 plus WD by WL into 1 minus alpha C divided by alpha C minimum. Right? So this equation we have to find out WD is a dead load, WL is a live load. Let's check. Now here is equation. Right? Put the all value in the equation and we can find out BS value is 1.01. BS means a correction. Correction is 1.01. So 1.01 means 1% correction is required for positive bending moment. So means we have to correction required for the positive bending moment is 1%. But this correction 1% means this is very small, very small. So we did not need to require this. If it is more than 5% or 6%, we have to require correction. But this 1% is doesn't need to be required. Okay, so we can neglect it. Correction will be neglected. Now we have to step for total design moment. We have to find out design moment. Now first thing we have to need a longer direction. Along longer direction. MOL means a longer direction. WLN by 8 we discussed it in the theory. IS 456 2000 page number 55. IS 456 2000 page number 55. Look at here. Here is equation. Clause number 31.4.2.2. MO WLN by 8. We write in MOL because in the longer direction. Okay. What is LN? Clear span extending from the face to face of column. Capital breaks the wall or but not less than 0.67 L1. W is a design load on the area L2 and Ln. L2 and Ln. Right? So we can write down W is a design load. So we have to simplify this to find out load. Let's do this. So capital W is a small w into L2 into Ln. We discuss it. Okay. So Ln is a clear span along Ln. L1. Ln is a clear span along L1. So clear span means 6 meter minus 0.4. 0.4 is a 400 mm column. So 6 minus 0.4 is 5.6 meter. So W, small w is 50 kilometer per meter square. So our equation will be converted WL to Ln square. So 50 into 4.6 to 5.6 whole square divided by 8. Okay, one condition here. Ln is a clear span. Ln is a clear span. But L2 is not a clear span. It's a regular span. Okay. Ln is a clear span. So we subtract a column. We minus a column from the regular span. Center to center distance, plus L2 is the center to center distance, right? So L2 will, as it is 4.5, 5.6 whole square, so moment is 264.6 kilometer into meter. Moment along longer direction, along shorter direction, same equation, but L2 L1 is changed because direction change, so L2 L1 also changed to Ln. 4.5 minus 0.3 is same. 0.3 is a column 300 mm, right? So MOS, so value moment along shorter direction is 198.45 kilonewton into meter. Moment along shorter direction 198.45 kilonewton into meter. Now step 5 we have to describe column strip and middle strip because moment will be distributed on the column strip and middle strip as well. So column strip along longer span. So column strip twice into 0.25 Ln, twice into 0.25 into 6000, so 300 mm. Why is twice into 0.25 Ln? Because column strip on the both side of the slab. Both side of the column. So 0.25 into L1 is only on the one side. It's only on the one side. Okay, I will explain the figure. Just give me some time. Okay, student. So you can see here is an interior panel. This blue line is interior panel. There is dimension 6000 and 4500. Okay. So in the fifth step, we have to calculate width of column strip as well as width of middle strip, right? I hope you understand what is column strip and what is middle strip. I will explain it in the video earlier. Okay, so now there is a one condition here. look at here. Here is a column strip. This all is a column strip, and center one is a middle strip. So calculate as a middle column strip for the interior panel. 0.25 L1, 0.25 L1 for the only for the one side. Okay, if for the interior panel there is only for a one side, but on the second side we have to also 0.25 L1 because we have a two column strip here, two column strip here. So that's why we have to find a column strip by a equation which is called column strip is equal to 0.25 L1 just for the one plus 0.25 L1 because we have a two side of column strip here for the one interior panel, right? So twice into 0.25 L1. This equation we put in the example, right? So column strip 2 into 0.25 L1, 2 into 0.25, 6, 300. So by the IS 456 2000 page number 53 clause number 31.1.1. Okay. Second 2 into 0.25 L2. Provided smaller of two values, we have two values here for the L1 0.25 L1 and 0.25 L2. In between whichever is smaller, we take as a smaller of two values. So width of column strip is 2250 because smaller is 2250, right? That's why 2250 is a column strip. So middle strip is equal to 4500 minus 32, so 22.50 mm. Okay. Now we have along shorter span. We found a column strip along longer span. Now we have a shorter span. So same column strip, width of column strip is same, but width of middle strip will be changed. 6000 minus 2250 to 6750 mm. Right? Column strip width in the both direction must be equal. So column strip will be same because L1 L2 direction is not changed, but just a direction is changed. L1 L2 value is same, but direction is changed. So column strip width is the same, but middle strip width can be changed. Right? You can see here 2250 column strip, 2250 middle strip, 2250 column strip. 6000 along longer span. Remember along longer span means in this direction, along shorter span means in this direction. Don't confuse in along longer span and along shorter span. Okay, along longer span means 6000 in this direction, and along shorter span this direction, right? Okay, so don't be confused along longer span and along shorter span. Okay. Okay. Now we are going to find out the moment. Okay. So total moment is 264.6 kilonewton into meter, and thickness is 175 mm. Effective depth is 175 mm. Okay. Column strip depth is 2250 mm as well as middle strip width is 2250 mm. Right? Now we have two things. First is negative, second is positive, as well as negative as well as positive. For the column strip positive and negative. For the middle strip negative and positive. Right? Now for the negative 0.65%, we discussed this IS 31.4.3.1. Negative moment is 0.65, positive moment is 0.35. Okay, for the whole interior span, for the whole interior panel. But we are calculate for the column strip. We are going to calculate for the column strip. For the column strip, 75%, okay, 75% of the moment, as well as for the positive 60% of the moment. Okay, and then after here is 264.6, 264.6. This is the moment. So multiplication by these two value, we can find out the moment 129 kN per meter and positive 55.6 kN per meter. Right? These are the moment calculation for the column strip. Now for the middle strip. Middle strip, same thing, 65% negative, 35% positive. Okay, multiply by 265.6, multiply by 265.6. Okay, and then after it will be subtract by this total column moment, total negative moment, as well as total positive moment, right? And then after we got a moment 43 kilonewton into meter and 37 kilonewton into meter. So these are the moment calculation for the column strip along a longer direction, column strip as well as middle strip. Okay, after find out the moment, we have one equation which is called PT, 50 FCK Fy 1 minus 1 minus 4.6 and mu upon FCK BD square. So by this equation we can find out PT. So here is a PT is 0.59, 0.235, 0.70 and 0.153. So by the PT's equation we have one more equation, AST BD by 100. So put this all the value in this, so we can find out total AST. Okay, the AST divided by meter means per meter length. Meter is 2 to 25 meter, width of column strip as well as middle strip. So by this equation we can find out 1032.5, 411.24 mm square, 297.5 mm square and 267.75 mm square. These are the design area of the steel on the tension zone per meter area. Right? Then after you can see there is a provided column strip for the negative 16 30 mm, 60 mm diameter, 190 mm center to center, 10 mm dia, 190 mm center to center, middle strip 8 mm dia, 160 mm center to center, 8 mm dia, 160 mm center to center. Right? So these are the design completed for the column along longer span. Right? Now we are now on IS 456 2000 page number 55 we have one clause here 31.4.3.2. in this moment we have one negative design moment 0.65 and positive design moment 0.35. means when we calculate a moment on a flat slab, negative design moment 0.65 and positive design moment 0.35 on where? On interior span, okay. So when we design an interior span, the negative design moment 0.65 and positive design moment is 0.35, right? But this is on the whole slab, but what we have to do, we have to find out a moment on the column strip as well as on a middle strip, right? So distribution of bending moment across panel with clause number 31.5.1 on a column strip, negative moment and interior support, negative moment on interior support, that an interior support, the column strip shall be designed to resist 75% of the total negative moment in the panel at the support. For the negative moment, there is a total negative moment, means by a 0.65% is negative moment and 0.65 is 0.75%. 65% is the total moment. Okay, I will explain in this way in the calculation, just give me. So look at here, okay, 0.65, let's zoom these things. Okay, yeah, great. 0.65 is the moment. So I can say there's a 65% of negative moment at the end and 35% of positive moment at the center. By this graph you can see this. We read in the IS code these things. Now there is a second point. They say column strip, on the column strip negative moment is 75% of total negative moment, means 100% of a 65 is the negative, and on the column strip this will be 75% on the column strip. Same thing for the positive, we have 60% for the positive. These things is writing in the IS 456 2000. Okay, here is a resist 75% of total negative moment. Same thing, yeah, for the column strip positive moment for the end each span. For the each span, the column strip shall be designed to resist 60% of the total positive moment in the panel on the column strip. Okay, so imagine there is a first criteria, this 31.4.3.2. There is criteria for the interior span only. For the whole interior span, there is a negative moment is 65%, positive moment is 35% for the whole interior span. But what we did it the column divide into column strip and middle strip. So on the column strip this is 65% and in 65 to 75% is on the column strip on the interior support, and as well as on the column strip positive moment is 60%, right? Okay, let's calculate this. Just remember this thing from the IS 456 page number 57 and 55. We have a two clause are there, right? Now we are going to design a reinforcement along shorter span. Okay, here is a MU 198.45 and effective depth 165 mm. Width of column strip 2250 mm, middle strip 3750 mm. Okay, so moment for the negative, for the positive, as well as negative for the positive. Okay, now first we calculate for the column strip negative and positive. So negative 0.65%, 0.35%, negative 65, positive 35. Then after 75% on the column and 60% on the positive side, okay, on the column strip. Okay, so by this value multiply by 198.45, so we got a value is 96.75 kilonewton into meter. It's a negative moment. 96.75 kilonewton into meter, it's a negative moment. But here you can see 1.01 is multiplication by positive. What is this? These are the correction. I can show you. Okay, yeah, look at here. 1% correction for the positive bending moment on shorter span, along shorter span. So these are the positive moment correction. So value is 42.1, right? Same thing for the middle strip point. Okay, then after here is a moment, minus 96.75 here, 42.1 here, and 1.01 is a correction. So value is 32.25 and 28.05 kilonewton into meter, right? And after we calculate the PT value is 0.49, 0.190, but on the middle strip we have to provide minimum 0.12 because value is below than 0.12 percentage. PT is not possible. So minimum requirement of the percentage of steel is 0.12%. So minimum we assume 0.12% steel on the middle strip. Okay, then after here is a total AST. So AST divided by meter, we can find out these values. Okay, AST per meter 808.44 for the column strip negative, right? 331.3 mm square AST per minimum for the column strip positive, 240 mm square for the middle strip negative, and as well as 240 mm square for the middle strip, right? So these are the design is completed along long span as well as shorter span for the flat slab. Okay, now we are on the step 7, check for the two-way shear. So check for the two-way shear is made along longer dimension. So for the critical section for the shear is taken as d by 2 from the face of column. So you can see in this figure this distance is d by 2 from the face of column, which is 300 mm. Okay, critical section for the two-way shear, right? So here is a d by 2, 82.5 mm. So VU is equal to 6 into 4.5. 6 into 4.5 is the dimension of interior panel, minus 0.565 into 0.465. What is this? Is the internal dimension, and these are the column dimension. It will be subtracted, multiplied by 50 Newton kilonewton is weight. So VU is 401.06 kilonewton. B0 is equal to total length of critical section, 2 into 565, 2 into, so 2060 mm is a B0, total length of critical section. Now we have an equation here, tau V is equal to VU upon B0D, 401 into 10 raised to 6 into 10 raised to 3. We find out here. Same thing for the 2060 is a B0 and D is a depth 165 mm. So tau V is equal to 1.16 Newton per mm square, right? And from the IS 456 2000 page number 58, 59, we have an equation there. Tau C dash is equal to Ks into tau C. So Ks is equal to 0.5 plus 300 by 400 is 1.25. So Ks is equal to 1. From where? From the IS 456 2000 page number 58, 59, right? Now we found a Ks value. We have the tau C dash value 0.25 FCK. So FCK is 20. So 1.1 Newton per mm square is a tau c dash value. Same thing for the tau v. So tau v is 1.18 and tau c dash is 1.1. So shear reinforcement is not required. Shear reinforcement is not required here for the flat slab design. So we have to going to design a shear reinforcement is consider 8 mm stirrups, 8 leg, Fe415. So ASV 8 into pi by 4 into square into 401. So if the shear reinforcement is in the column, okay, this shear reinforcement is in the column, then this shear reinforcement is required in the slab, right? So Vu is equal to Vu minus 0.5 tau C BD KS is from the IS 456 2000 page number 59. Let's check this equation. So here is IS 456 2000 page number 59. Okay, we have one clause number 31632 where the shear stresses are critically sectioned exceed the value given in 31631, which we have already calculated shear reinforcement check. Okay, but less than 1.5 tau c shear reinforcement shall be provided. Okay, if the shear stress exceed 1.5 tau c, the flat slab shall be redesigned. Shear stress shall be investigated at a successive section more distance from the support, and shear reinforcement shall be provided up to a section where a shear stresses does not exceed 0.5 tau c. While designing the shear reinforcement, the shear stresses carried the concrete shall be assumed to be 0.5 tau c and reinforcement shall carry remaining shear. So there is a no direct equation here. There is one clause which is called 31632. In this clause we have one line. Okay. So by this line from the IS 59 we have described this equation. Okay. Now Vu we have 401 into 10 raised to 6 into 10 raised to 3, 0.5 tau c 1.1, 2060b. Okay, 165 depth, Ks is 1. So Vu is 21241 into 10 raised to 3 Newton. Now by this Vu equation we can find out spacing 0.87 Fy ASV upon D, 0.87415 into 204 into 165, okay, divide by 21241 into 10 raised to 3. We have a SV value is 112.74 mm. Okay, to imagine we can say provide 110 mm spacing. Okay, that's why we provide 8 mm dia at 8 leg stirrups at 110 mm center to center. Provide shear reinforcement up to 300 mm from the face of column. So 300 plus 110, so 3.72 means 4 stirrups are required. 4 stirrups are required. Right? Now we have some sketches to draw. Let's draw some sketch. So here is a sketch. Drawing is completed. Detailing of the interior panel design. You can see here. Okay, let's zoom this. Yeah. Look at it. It's a column strip here. Dimensions 60 mm dia, 240 mm center to center. Middle strip 10 mm dia, 90 mm, 190 mm center to center. 8 mm dia, 200 mm center to center. All the things are designed and detailing is completed here for the interior panel. And as well as I draw one sketch, one section of a middle strip. Okay, so you can see 8 mm dia, 160 mm at the top and 8 mm dia, 160 mm at the center at the bottom. Same thing for the 8 mm dia at 200 mm center to center along shorter span, and 10 mm dia 240 mm center to center along shorter span, and 6000 mm is the distance between two columns. So here is the sketch is completed. I hope you understand how to design a flat slab without drop and without column head. So design of flat slab is completed without drop and without column head. Now here is our practice question. Now you can see there is a one question is describe advantages and disadvantages of a flat slab, and this question is asked so many times in exam. So many times in exam in the 5 to 3 marks, okay? 5 to 3 marks, but so many times. And here is a one practice question. There is a design an internal panel of a flat slab, panel size 5 meter by 5 meter without providing drop and column head. Size of column is 300 mm by 400 mm. Live load 4 km square. Floor finish 1. Height of column 4 meter above and below. Use M20 grade of concrete and Fe415 grade of steel. Okay, and this question is asked in May 2017. Right?